So this is a quick walkthrough of how to use a Raspberry Pi Pico with the PicoBricks IDE. So this is the documentation. This is the ultimate starter kit for Raspberry Pi Pico. The documentation is pretty thorough. This is just to show you the components. So on the right, you see this is the board. And there's a lot of sensors that come with it. The buzzers, you have LEDs, you have resistors, 220 ohm. You have a breadboard where you attach the components to, right? So you don't have to physically solder the wires together. And it really goes through in a lot of detail. Okay, so this is handy to have. If you purchase the kit, you can always refer back to this. All right, so quick setup. It's always good to just make sure everyone's using the same hardware so things get less confusing. So this is the Pico microcontroller. This is basically the computer that you're going to use. It's a mini computer, so it's not as powerful as like your PC or your laptop, but it can control devices, which is why we use it. It has these metal pins on the bottom. Sometimes you can buy it without these metal pins soldered onto it, basically attached to it, the board. But when you buy it with the board, it's much better because then you could just physically push it into your breadboard like this. And because all these holes on the board are connected, when you attach a wire to it, you are attaching components to this computer. Okay, so now the Pico is attached to the breadboard. That's this white piece with holes in it. Bear with me if some people might be very familiar and others not so much. Okay, so just a simple LED setup. So how does that look like? There's the LED. One thing you basically have to know is that LEDs have a direction to them. One leg is positive, one leg is negative. How do you know? The long leg is the positive end. So if you were to look at a brand new LED, it would be straight and it would be clear difference. In this case, this is my long leg of my the LED that's going to light up. So you just place this somewhere on the breadboard that is easy to attach to, right? So I'm going to decide to do that here. Okay. Now you have to basically add a resistor. What is that? That's this component here. It slows down the electrical current coming from the power supply, which is the computer, so that it doesn't burn out the LED. So I'm going to attach it to the small leg of the LED. Notice that my larger leg is on. This would be column 25. And the smaller leg is about on 29, right? So to the small leg of the LED, I will attach the resistor, one end of it. They're both essentially the same exact thing. I just bend them and attach one leg of the LED to one leg of the resistor. The other leg of the resistor I put across the little trench in the middle and attach it to this other side. Then I will take a jumper wire, which is this male jumper wire, male because both sides have pins, male, and attach the black jumper wire to the other end of the resistor, right? It's in the same column as that end of the resistor, which is 29 on this side, right? And then I will just bring it over here to this what's called a rail, and we'll make this the ground rail. Okay, now this part is if that was a little bit confusing, this will definitely be confusing because we'll have to know what these different holes mean for this device, and they have different meanings. So the way we understand that is we have to look at what's called a pin map. So let's bring that up. So if we go to any basically page that has a pin map, it is basically going to show you something like this. It's going to show you your board with a couple of numbers on it. Each of these numbers corresponds to a physical location on the board that you can attach wires to. And you have to know these numbers, what they are, so that when you're attaching things to them, you get the right results. And also you can use those same numbers when you're doing coding later. So for us, the only numbers we really care about are the ones that we're going to use. So we're going to decide to use GP20. This is physical pin 26, and we're going to remember that. So again, it's GP20, physical pin 26. That pin is 1, 2, 3, 4, 5, 6 holes or places up from the bottom. Okay, so let's return back. If you look here now at the board, when we're looking at this board now, we need to basically count up 6 positions. 1, 2, 3, 4, 5, 6. That is physical pin 26, I believe, and GPIO pin 20. Okay, that's what we need to remember. So from that pin that we chose, we attach a red cable that tells us that power is going to come out from here, and attach it to the other leg of the LED. What's missing here? So now we got the power from the device to the sorry about that, to our LED. What's missing is that we don't have the computer grounded, right? So we need to have a circuit, we need to have a ground and a power source, and all components need to be sharing the same ground, right? So if we look back on that map, we would notice that the third point up was the ground. So 1, 2, 3, that is the ground on the board, and we share the ground with the LED. So I'm going to attach it to this rail here. So now they are sharing the ground. Now there is a ground to share, and that's where the voltage is 0. So all the current goes in through this red wire, into the LED, into the resistor, back through the black cable, and returns back to the board through this ground, right? So power comes in, runs through the LED, into the ground, back to the board, right? That's a circuit. Okay, now let's see if we can code this up using PicoBricks. All right, so we're in the PicoBricks IDE. So the first thing is remember that this IDE requires that you connect your device to your computer. So I'm going to flip back to the board so you can see what I'm doing is I'm connecting a micro USB on one end and a USB on the other end, right, to my laptop, right? And that is going to basically power the board. Now the board is going to receive power from the laptop, and it's actually acting like the external power source. My laptop is. Now everything is powered up. What's more important is that if you go back into the IDE, the development environment, you can click these two little sort of connectors, these plugs, and now you're going to see that there should be something up here for you called board CDC. The COM may be different. It could be COM 5 or 4 or some other number, 7. Mine is COM 8, and I hit connect. Yours might not say paired initially, but eventually it will. All right, so we're all connected. So how do we know we're all connected? Well, there's a couple ways you can test that. The first is here, that in this monitor down here is the printout is telling me that it's detected my device, the Raspberry Pi Pico 2W RP2350, and that makes sense because that's what I connected. The other way to test it is to just code up a program and run it and see if it actually works. So we're gonna do both. Okay, so let's start by putting a brick down there. This Pico brick basically is a starter so that it understands the rest of the pieces. So it's basically the starter block. And what we want to do is, first off, when you're writing something like this, is you always want to sort of write a comment so you keep in mind what you're trying to achieve. Test Pico connection link LED, right? So just keep in mind what are we actually trying to achieve here, okay? And okay, so next, you can see on the PicoBricks there are a lot of pre-made blocks. These are all these blocks, and the one we want is called digital pin right. Digital pin right. We also want to remember that we chose a specific pin on the Pico. Remember that was GPIO pin 20 based on the pin map. Remember the red wire was connected to something. That position is called GPIO pin 20. We need to tell PicoBricks that that is where we plugged in the LED to, right? That is LED positive terminal. That's how we wired it, right? These are just notes I'm writing so that I understand what I connected and what I'm trying to achieve. So the Pico pin 20 is connected to the positive terminal of LED. So I need to change this pin to 20, right? This 0, P0 tells me if I want position 1 or position 0, which basically means on, 1, and 0 is off. So I want to write it to be on, right, to test the LED and turn it on. After I do that, I want to turn it off, right? So just have it blink. If I wanted to repeat this, what would I do? Now, there's many ways to do a loop, but the pretty stable and consistent way to do a loop in this context is to do what's called a while loop, and in PicoBricks that's called forever. So it just continues on and on because it's always going to be active. And the only way to know why that makes sense is to look at the Python code. If you look here, it says when I put down this forever block, and I show the Python code that these blocks are running underneath, that said while true, and true is always true. So it's basically saying do this all the time. So do what all the time? Turn on pin 20 and then turn it off. Keep repeating that continuously. You need to add in a little wait between these because it's just there's going to be too many commands flooding the computer and it won't actually work. So you need to add a pause in between when the light is on. You add a break so it stays on for a little bit and then it shuts off. So we'll add a 1 second on and 1 second off. That actually should be enough. So let's see. I could be wrong, but let's see. This is the best part is you get to test. Okay, so while this is up here, I can see if I can get the okay, so basically I'm just going to run it right now. Run. And there you go. So not a big problem. We saw that we were able to wire it up pretty quickly. We have the pin 20 being used, which is physical pin 26 on the Pico 2 board, Pico 2W board. We knew that because we referenced the pin map. We connected a red wire from that physical pin 20 to the long leg of the LED. And you can see that here. And then we added on the other side a resistor 220 ohms, so make sure we don't burn out the LED by running through much power current through it, and the remaining wires. So that's how you wire the LED, and also how you code it up in PicoBricks, which is a block-based visual programming language um, to control physical devices like the Raspberry Pi Pico. So this is the second part of the tutorial, just showing you how you can control a Raspberry Pi Pico microcontroller with the PicoBricks IDE. And so what we're going to do here is going to build up onto the LED circuit we had built previously. So this, what you're seeing here is the Pico 2 microcontroller in green attached to a breadboard, and we wrote a program in PicoBricks that would basically turn on that light using that PicoBricks block-based IDE. So we're going to add to this and now use what you see here. It's called a sound sensor and a buzzer to make a little kind of alarm system. And we're going to do that by basically adding those components, the sound sensor and the buzzer, onto the existing Pico plus LED system. So I'm going to take us step by step through these parts. The first part, as I said, is the sound sensor. It's the main component you'll need that will actually detect the vibrations when sound is detected and turn those into a signal that will be read by the Pico. So when sound comes in, the Pico is going to register that sound and send a signal to the buzzer to make a noise to tell us that a sound was heard. And that noise will also trigger the LED to turn on, because the buzzer and the LED are going to be sharing the same power output from the Pico, and we'll see how that comes together. Okay, so let's start with that background. Just take a quick look while we have is the Pico 2 kit. So we have this kit, and this is what we've been working with. This is how we have access to all these parts: the LED, the resistor, the board itself, the Pico 2 board, right? So it's very convenient because without the board, none of the components work. So the Pico 2 board is the brain that's actually allowing these different components to communicate with each other, and for us to write code to load onto the Pico board for it to be able to do these things. Okay, so the kit has everything in one place. I believe the price at this point is $51 on Amazon. You can see here where we have the sound sensor, the USB cable that physically connects the board to your laptop while you are programming it, the wiring, right? All these parts, the breadboard where you physically attach your device to. Okay, so the documentation is pretty clear, and they have some examples there. So this is from 52Pi, Ultimate Starter Kit for Raspberry Pi Pico, and this is the hardware I'm using. So this is a page from Core Electronics, another good resource, just showing you the close-up on the sensor module itself. You can see that there's 3 pins, right? These 3 metal connections. VCC, that's the power. Ground, that's where the circuit is going to return to complete the loop to the ground. And the out, right? This is where the data comes out and goes into our Pico device. So the sound is registered on one end, and the signal is sent out when that sound is detected through this pin. The buzzer is another component we'll be using. We'll be using what's called an active buzzer. It's going to basically make sounds when a current passes through it, and it has a positive end and a negative end. The only thing you really need to know here is that the positive end is going to be longer, physically longer, than the negative end. Okay, so we just need to keep track of which is the positive and the longer end. So let's go back now to our physical setup here and just look at this buzzer, right? In the buzzer, there's two pins and there's one that's physically longer. That is the positive one we were looking at earlier uh, in that diagram, okay? So with that, let's just plant this buzzer onto the existing circuit. We'll do that by remembering that we chose the GPIO pin 20. In our previous video, we chose where you see this red wire that is connected to the Pico in GPIO pin 20. That's where that row, this hole, corresponds to on the pin map for the Pico. The pin map, if you remember, looks like this. So on this where you see my cursor, that GPIO pin 20 is there's a red wire there on our physical setup at it corresponds to GPIO pin 20 or physical pin 26 on the Pico device to our where we have our red wire here on row 15. Okay, so that's the pin that is going to send the signal from the Pico to the buzzer. Okay, so how do we actually do that? So we're going to take the long terminal here, the long pin, and we're going to line it up on the same row, which for the red wire is row 25. So here where the red wire is, okay, that is where we're going to put the long leg. The short leg is going to sit into the ground rail, which is where these black wires are going into. This is where the circuit returns back. So this entire row, this entire rail back here, where I have these black wires going into, is going to be where the short pin is going to go. Okay, so that we'll set that up. Long leg into 25, getting the signal from Pico, and short leg into the ground rail. So that's done. Now let's go to the sound sensor. The sound sensor, as I said, has 3 pins. The first one, it's going to say VCC, and we're going to connect a red jumper wire to VCC. This is a female male, so the female end into the pin. The male end is going to go into the Pico. So in the Pico, we need to understand that there is a spot for power. A pin for power is called VSys, and that's going to be row 2, right? Row 2 for us. Okay. So now we have connected the power. Now the next is to connect the data. So we'll do data is the out pin, with a pin that's marked, it said out. And we'll bring that into, this is going to be GPIO pin 20, which is row 7. So I had to refer to the pin map to know that this is GPIO pin 28. And that is row 7. Okay, so now the sensor and the Pico are connected. So now we have the last pin, which is the ground, right? And it has to share the ground with our existing circuit. So we're going to put it into any of these pins that are on the ground rail. Now all 3 pins are connected. So that's done. Okay. So I'm just going to rearrange this a little bit so it's easier to see, like this. Okay, something like that. And you can see all 3 connections are made. You can see the buzzer is getting the power from the Pico, this red wire, and the sound sensor is connected to VSys. which is row 2. Okay, so that's done in terms of the wiring. Now we need to test. So we're going to do that in PicoBricks. So we're going to return back to PicoBricks and let's start fresh. I'm going to delete what we had done, and we're going to start fresh. So basically, we always start with this PicoBricks block, and we basically, it's always good to write down the goal. So it's not, the goal here is different from previously. The goal is to make buzzer sound or activate buzzer okay. The previously we had the LED connected to GPIO pin 20. That's still the case, but we need to add the new information, which is that the sound sensor is on the out of the sound sensor is connected to GPIO pin 28. Why do we write this here is because when we are coding this, we're going to need to refer back to those pins 20 and 28. Okay, so how does this work? We need to have a way to write this in plain English so that we will basically have something to aim for. So if sound is detected by sound sensor, then turn on buzzer on pin 20, right? What is not obvious here, and I didn't add, is that both the LED and the buzzer are sharing the same pin. So they're actually wired in parallel. But basically what that means is they are sharing the same pin. So we're going to write buzzer positive. Okay, that long leg of the buzzer is connected to the same pin as the LED. All right, so when then turn on the buzzer. The next thing is if or else is it's actually technically an else. So if no sound is detected, no sound detected, then we want to turn off the buzzer. Even though the buzzer will not be on, we just want to make sure that the default is off, right? So it's off. If there's no sound detected, the buzzer is basically told to stay off. This prevents things like the buzzer getting stuck. Okay, if you randomly exit the program or the program just crashes. Here we go. Well, so the next thing is the forever loop. So you might have seen in the previous video, I referenced the forever loop. Forever loop, basically, when you put this block in, so this whole set of blocks here are called loops. Loops are basically ways to make your program do the same thing over and over and over, which is something that computer programs are very, very good at, repeating things. So exactly the same every time. So forever basically means repeat something over and over without stopping. So in Python, in the language that's underneath this, forever means while true. That's just the text that is underneath this block when it's running. Okay. Not that important right now. Main thing is that this block is going to tell the program to continuously run the same thing over and over. Yeah, sorry, I was a little bit far away. If you kind of had trouble seeing that, I can sort of run it back. This is the forever loop that we're using to have this basically keep repeating this entire check for the sound sensor. This is the read pin where the sensor is connected to on GPIO 20. This is a 0 because the sound sensor value actually is going to be returned as a 0, meaning it detected a sound. This other one is called a write. Again, it came from this basic set, and it was on pin 20 because set to pin 20 because the buzzer's on pin 20 and the LED. And we set this to 1 to turn it on, keep it on for 0.3 seconds, turn it off, wait 0.1 seconds before trying this again. And then finally, we want to turn it off, turn the buzzer off. So that's like the default if nothing is happening. The other thing you want to do is, it's in this case, the buzzer being just turning off on and off so quickly is not that obvious to recognize that. So just from experience, we're going to add a repeat in here. So what this does is basically what it says, it's going to repeat this buzzer turning on 5 times. So it's going to on and off 5 times. If a sound is detected, turn the buzzer off, on and off 5 times. Right? That's a very distinct pattern. So you'll be able to recognize what's happening very easily because this is a very specific thing that's going to happen. A buzzer turning off 5 times it's hard to not know what that alarm is about, right? It's about recognizing the sort of the pattern that you have implemented here versus just a one-off on and off. That is kind of hard to distinguish from all the other noises in the environment. All right, so the next thing is, because it's going to repeat on and off 5 times, you kind of want to once that's done, set this to turn off again the buzzer. So just to ensure that once we repeat it on and off 5 times, the default after that pattern finishes is to shut it off, and then it would go back to checking again, right? So if nothing is happening else, keep the buzzer off. Now the other piece here, last piece, is that we need a way in plain English to tell us what's happening without us having to like physically wait for things to happen and like listen for alarms. Things that give us written messages. So that's where you use these serial print blocks. These are just print statements that the program will print out and just give you a message. So in the beginning, when we get this first sound coming in, we want to say sound is detected, right? That's useful because now we have a written message that tells us what place in the program where we are, right? Once this prints, we know we're in this part. It just detected a sound and it's telling us that actually just happened. Now the next thing we want to do is we want to add another print statement down here, which tells us that no sound is detected, which also tells us that where in the program we are. So this is going to tell us that it's not detecting a sound. Both of these are important because you want to know if your setup is working, your code is working, and based on which one you see, you'll know where in the program your code actually is. And you'll see that down here in the serial monitor. So this is the live messages that will be running when you run your program. Okay, so that's a lot of background. I apologize for that. We're gonna hit run, but before we do that, always want to make sure your device is connected. So I don't have my device connected, so I need to do that. You see here, I have the micro USB, but I don't have the actual USB connected to my laptop, so I'm gonna plug that in now. Okay. You'll see that the sound sensor lit up, right? And it's also responding to my voice. Now, why isn't there an alarm right now, even though it's responding? You'll notice that there's a constant LED that's not changing in brightness, and there's one that is changing in brightness. The one that is changing is the indicator of sound, that it is detecting sound. The other one is just a power indicator. It's getting power, so that's good. We know that it's detecting the sound vibrations and it's also getting power. But it's not, there's no alarm. Why? Because we haven't ran our code. So we just got a bunch of parts connected, but the computer doesn't know how to interpret that yet until we load our program onto it to tell it what to do when it when these things are happening. Okay, so going back here to run it, now that we have it connected, physically connected, now we go to this button up here I just pressed on. You find your board and hit connect. You'll see there's a message on the terminal that will tell you that it was connected, right? This is the device I have connected, and it's a Raspberry Pi Pico, right? And then we can hit run. Okay, so let's see here. Go back. All right, so I don't know if you noticed there, but basically there was an issue where we were telling the computer to print no sound is detected when after checking if there was no sound, if the computer found that there is no sound, it would jump down here to the else statement and print. Now it was doing that as fast as it could because why? Because we didn't add another wait between the next time it would check again. So it's basically running this as fast as it could, and that was consuming all the resources. So obviously that's not the right way to do things, and that basically caused the computer to get stuck. So how do we fix that? Well, we just have to add another wait statement. So let's do that. Let's add another wait statement right there, and that will fix the problem. It will have time to breathe and basically have time to check the pins to see if there's actually sound coming in. All right, so that was the issue that was causing the printed thousands of messages because it was just running at this else as fast as it could possibly do it because it wasn't detecting any sound, and basically that got all the resources stuck doing that one thing. All right, so that should fix the issue. All right, so now we solved this problem. It should be able to work. So we'll just reconnect here. Yeah, let's see. It's not detecting the Pico. So make sure. Oh, I don't have it physically connected. Okay, that makes sense. All right. All right, so let's switch back to now trying to connect. Everything is all good. See our message that it's connected. All right. Now the next step is to basically do a demonstration. So you can see that when I'm speaking, there's a light that's pulsing. That is the sound being detected by the sound sensor, and there's a constant light that's always on. That's the power to the sensor. So when I'm speaking, you'll notice that the buzzer goes off. That is the job of the computer to take in that input from that white grayish cable on GPIO pin 28, read it, and tell the buzzer to turn on the alarm. Okay, so hopefully that makes sense. We can see here that when I'm speaking, most of the time, there's no sound detected, but when my voice is loud enough, it will detect the sound. All right, so the buzzer is working as expected. This is the behavior we expect. Pretty cool. All right, so I hope you guys enjoyed this.